Hey, welcome to the second video in class number 10. In that first video, we looked at what we called deep geothermal. So that was the flux of energy from radioactive decay from the Earth's deep interior. In this video, I want to follow up quickly with a totally different kind of geothermal energy. And we're going to call this shallow geothermal. And this refers to basically heating your house or cooling your house by pumping water into the subsurface in pipes where it can exchange heat with rocks in the subsurface and bring back either colder or hotter energy depending on the situation. So this is kind of a heating method for homes that involves the shallow subsurface. And it's important because this, like other things we've talked about, is an important source of carbon-free energy. So let's jump right into it. As I just said, shallow geothermal is a method of exchanging heat energy with rocks that are just below the surface. So that would be about 10 to 100 meters depth. And what's important about that depth is that if you look at temperatures at a 10-meter depth, what you see is that they perfectly mimic the mean annual temperature. Okay? So this is a contour map of temperature at a depth of 10 meters below the surface, and it mimics the mean annual temperature. So down in Florida, it's around 77 degrees. Up here in Vermont, it's around 45 degrees down there. So that's very different. It's a 30-degree difference, and basically has to do with the fact that the average temperature in Vermont is much colder, and the subsurface is mimicking that. So how does this give you a net energy benefit? Well, the basic idea is that if the mean annual temperature is here, somewhere around 45 degrees Fahrenheit, and the annual temperature is doing this, very cold in the winter and then warm in the summer. Okay, so this red line shows kind of the highs, this shows the lows by month. So the monthly temperature is kind of coming somewhere in this band right here. So basically in the summer, the surface temperature is way warmer, roughly 30 degrees warmer than the ground. In the winter, it's roughly 20 or 30 degrees colder than the ground. Okay, so in the winter, the ground can actually provide extra warmth, and in the summer, the ground can actually cool things down. And that's the idea. So how do we actually get that heat energy out of the ground and into our houses? Well, recall from the previous lecture that the flux of heat depends on the conductivity of the material, that's K, the area that's in contact, so that would be A, and this final term, the thermal gradient. So that's the difference in temperature divided by the length, or the distance between the two objects. So we're going to get a higher heat flux if we can either increase this thermal gradient, or we can increase the conductivity, or if we can increase the area of contact A. Okay, so here's a bit of a different look at some of these temperature differentials. What this plot shows is temperature difference relative to the mean. So this would be 20 below the mean, this would be 20 above the mean. And then as a function of depth going down below the surface. So this is kind of a cross-section looking into the subsurface. And what we see is that in the winter, the surface is 20 degrees colder and the profile increases down to the mean annual temperature, reaching that by about 25 feet depth. Now, what's really happening here is that the thermal conductivity basically is not high enough to bring this deeper area into equilibrium with the surface fast enough. So in other words, heat is escaping because it's colder up here, but it can't escape fast enough for a given thermal conductivity. And that's what causes it to go down to the mean here with depth. Now you'll also notice that these profiles aren't the same shape. They're a little bit different in shape. And that depends on the material that they're made of. So notice that the wet soil actually is a little bit colder at a given depth below the surface than the dry soil. So the wet soil is a little bit colder at 8 feet than the dry soil is. And that's because the wet soil is a much better conductor. It has a higher K, or conductivity, which means that it can release that heat sooner, more effectively, and actually cool down quicker as the seasons are changing. So you end up with a profile that's a little bit colder in general. And then of course you've got the inverse of that over here. That profile is a little bit hotter in the summer. But the main point is that none of these materials have high enough thermal conductivities to actually equilibrate with the surface, which is why the deep surface always mimics the mean annual temperature. So as a final slide, how do we actually drive the exchange of heat energy in these systems? It's typically done by burying a bunch of pipes somewhere below 25 feet. And we then pump water or other fluids through the pipes, and they exchange heat with the rocks and bring it back. And so the idea is that you want to have a lot of surface area on your pipes, okay? Because we're going to increase that area A, which is going to increase the heat flux into and out of the pipes. Of course, also by bringing that water right down in to the subsurface, we're decreasing the conductive distance. So we're putting a cold material right next to a hot material, and that's going to drive higher heat fluxes also. So I'll leave you with a couple concept questions here. There's no quiz for this video, and please join us for Friday for sedimentary rocks.